This is problem set number 8, problem 1. In the figure, each capacitance C1 is equal to 6.9 microfarads, and each capacitance C2 is 4.6 microfarads. Part A, compute the equivalent capacitance between points A and B. Part B, compute the charge on each of the three capacitors nearest A and B, nearest point A and point B, when the voltage between point A and point B is equal to 420 volts. And part C, with 420 volts across point A and point B, compute the voltage between point C and point D. Okay, before I answer part A, I just wrote down something from chapter 24.3, combining capacitors, and it's just about capacitors in parallel versus capacitors in series. Okay, so for capacitors in parallel, there's two things we have going for us, and that's that the voltage across each capacitor is going to be the same. So the voltage of C1 is going to be the same as the voltage equal to the voltage at C2. Okay? And the second thing we have going for us is that the equivalent capacitance, right? If I add these two capacitors together for capacitors in parallel, is just the sum of each capacitance. So C1 plus C2 would equal to C equivalent for capacitors in parallel. Okay. For capacitors in series, the charge on each capacitor is going to be the same. So the charge on capacitor 1 is going to be the same as the charge for capacitor 2. And the equivalent capacitance, the inverse of the equivalent capacitance is just 1 over C1 plus 1 over C2 plus 1 over C3 plus, and so on and so forth, right? And lastly, the potential differences, or the potential difference for this circuit is the sum of each capacitor's potential difference. So the voltage at C1 plus the voltage at C2 is going to be equal to delta V, total delta V. Okay? Okay, so back to part A. Find the equivalent capacitance between points A and point B. So I'm going to draw my circuit. Oops. Okay, so I have C1, 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 oops. Got C1, C1, and C1. Then I have C2 and C2, okay? And they stated that C1 is equal to, so C1 is equal to 6.9 microfarads, C2 is equal to 4.6 microfarads. Okay. So I'll work on this, combining my capacitors from the right side of the circuit going all the way to the left side until I have a single capacitor, or single equivalent capacitance, okay? All right, so I'll start with these three capacitors in series right here, okay? So again, for capacitors in series, I'm going to use this to add them all up. So I guess I'll use orange. So my equivalent capacitance is going to be equal to 1 over C1 plus 1 over C1 plus 1 over C1 to the negative, to the negative 1, right? Because it's supposed to be 1 over C equivalent is equal to this. And that's for these guys. Okay, they're in series. But instead of using this fraction and having my C equivalent in the denominator, I'm going to take the inverse of both the left side of the equation and the right side of the equation so that I can just have C equivalent on the left side. Okay, so get the inverse of that. Okay, so that's going to be equal to 3 over C1 to the negative 1, which is equal to, that's equal to 3 over 6.9 times 10 to the negative 6 farads to the negative 1. And that's equal to my C equivalent, which is going to be 2.3 microfarads, right? Or 2.3 times 10 to the negative 6 farads. All right, so I will plug that in. Actually, I might be able to just copy paste this so I don't waste too much time. Copy, paste. Okay, and then I'm gonna erase this and erase that. And so now my C equivalent is I'll use this color. So C equivalent equals 2.3 microfarads. Okay. Next thing I have to do now is I have two capacitors in parallel, right? And I'm gonna put them together. So according to this chapter 24.3, for capacitors in parallel, I just need to sum up the capacitance across each capacitor, and that'll equal to my equivalent capacitance. So for the next one, C equivalent will be equal to, put a line across there, so C equivalent now will be equal to C2 plus 2.3 microfarads, or that's equal to 4.6 microfarads plus 2.3 microfarads. So now my C equivalent will be equal to 6.9 microfarads, okay? So let's do that again. Okay, so now this will have a C equivalent of 6.9 microfarads. All right. So again, now I have 3 capacitors in series, right? So I will get the equivalent capacitance just by this part of chapter 24.3. That the inverse of the equivalent capacitance is equal to the sum of the inverse of each individual capacitance, right? All right, so C equivalent for the next part is going to be equal to, sorry, I'll write that better. So 1 over C equivalent is equal to 1 over C1 plus 1 over C1 plus 1 over this equivalent capacitance right here, which is 6.9 microfarads. Funny enough, that's also equal to C1, right? Because C1 is 6.9 microfarads. So really, we're going to have 3 over C1, which is also equal to 3 over 6.9 microfarads. But instead of using 1 over C equivalent, I'm going to take the inverse of both sides of the equation. Okay, so that I get C equivalent is equal to, C equivalent will be equal to 3 over 6.9 microfarads to the negative 1 power, okay? And that will be equal to, again, 2.3, okay? Microfarads. So C equivalent equals 2.3 microfarads. Okay, so here I have C equivalent equals, again, 2.3 microfarads. All right. And now to get to the next step, let me just make this a little smaller so we have more space. Okay, now to get to the next step, we have 2 capacitors in parallel, right? So we will just sum them up to get the equivalent capacitance for that. So here, C equivalent will be equal to C2 plus 2.3 microfarads, which is equal to, C2 is equal to 4.6 microfarads plus 2.3 microfarads. So that is equal to 6.9 microfarads. That's the answer there. So just rewrite this or redraw this. Copy. Paste. That will be equal to 6.9 microfarads, right? All right, lastly, just to get the equivalent capacitance of all this, we have now 3 capacitors in series. So for capacitors in series, we're going to use this to get the equivalent capacitance, as we've been doing. So C equivalent is going to, or again, 1 over C equivalent is going to equal 1 over C1, right? Plus 1 over C1 again, plus 1 over the equivalent capacitance, which is 6.9 microfarads, which is also equal to, this is actually also equal to C1, right? That was given in the problem. So that will be equal to 3 over 6.9 microfarads is equal to 1, is equal to 1 over C equivalent. So I'm going to take the inverse of both left and the right side of the equation. So then I'm left with C equivalent is equal to, and I'm just going to plug this in my calculator, and that's equal to 2.3 microfarads. Okay. So then for part A, the equivalent capacitance between points A and point B is equal to 2.3 microfarads. All right, and this is going to be my final answer for part A. All right, I'll draw a line there. Okay, part B. So part B, compute the charge on each of the 3 capacitors nearest to point A and point B when the voltage across point A and point B is 420 volts. Okay, so now I need to compute the charge on each of these 3 capacitors nearest to point A and point B. So this, and this. Okay, we'll find the Q, or the charge, for those 3 capacitors. Okay, so since I am most interested in these 3 capacitors, I guess I'll just copy and paste this guy. Okay, so this is coming from part A, right? I just copy pasted this from part A. And from part A, I already know that the equivalent capacitance for the rest of the network right here is 2.3 microfarads. I'm just going to add these 2 capacitors, combine them, I should say, okay? So if I combine them, that would be A okay, so this would still be C1. This would also still be C1. Lower that a little bit. And then this would be C equivalent right here. Okay, I'm going to find out what that is. So I have C equivalent is equal to, since they're in parallel, since these 2 capacitors are in parallel, all I need to do is add them, and the sum of those 2 capacitors, the capacitance of those 2 capacitors, is just going to give me my equivalent capacitance. Okay, so That's going to be C2 plus 2.3 microfarads, which is equal to 4.6 microfarads plus 2.3 microfarads. So that's equal to 6.9 microfarads, right? Okay. So now I have 3 capacitors in series. Okay. And looking back at that little note I have from chapter 24, section 3, for capacitors in series, the charge on each capacitor is the same. So I know that the charge here is going to be equal to the charge for this capacitor and also the charge for this capacitor, right? What else do I know? So these are also, since these capacitors are in series, I also know that the sum of the potential difference for each of the 3 capacitors that I have should equal to 420 volts, right? Because that is the voltage between point A and point B, 420 volts. That was given. Okay. So let's do some work. Since the sum of these, the voltage for this capacitor, the voltage for this capacitor, and the voltage for this capacitor has to equal 420 volts, right? And they each have equal capacitance, as we can see, right? C1 was equal to 6.9 microfarads. So the C equivalent has 6.9 microfarads. C1, obviously, that's equal to 6.9 microfarads that was given in the problem. And I know that I have here, I have V of, what was it? Okay, so VAB is 420 volts, right? So I know that the voltage here is 420 volts. Actually, I could just write that down. So delta V equals 420 volts. So then the sum of the potential difference for each of the capacitors in series is going to give me 420 volts, okay? And recall from chapter 24, section 1, so chapter 24, section 1, the definition of capacitance is equal to charge over potential difference, okay? Like I said, right now we have equivalent charge or equivalent capacitance between all 3 capacitors in series. And we know that the charge between all 3 capacitors in series is the same, right? That's here. Charge on each capacitor is the same, and they're in series. So then delta V for each of these guys will also be equal. What else do we know? We know that the delta V for each of them has to equal 420 volts. So we could just do 420 divided by 3, right? To find the voltage for each one. Let me just delete this highlight. So delta V for each one is equal to 420 volts divided by 3, which is equal to 140 volts. Okay, so I know the V here is equal to 140 volts. V here is equal to 140 volts. And V here is equal to 140 volts, right? So now I can find my charge. And I know, again, the charge is going to be the same for all three capacitors. Charge here, and charge here, okay? Which is obvious since the capacitance is equal and the voltage is equal for all three of them, right? So Q is equal to C, capacitance times, capacitance times delta V, and that is equal to 6.9 microfarad times 140 volts, and that will give you 9.66 times 10 to the negative 4 coulombs. Okay, so that is Q on each capacitor. And I'll write that down with green. Let me move that down a little bit. So Q is equal to 9.66 times 10 to the negative 4 coulombs. And Q here is equal to 9.66 times 10 to the negative 4 coulombs. And the Q here is equal to 9.66 times 10 to the negative 4 coulombs. Okay. Actually, what was the question for part B? Compute the charge on each of the three. Okay, yeah. So this is the charge for each of the three capacitors nearest to point A and point B when the voltage between point A and point B is 420 volts, okay? So there is your final answer for part B.